Hello everyone, I'm Nick, and I'm here with Mike, Gurjeet, and Jess, and our project is SpineGuide. Imagine you're a resident in orthopedic surgery about to perform a spinal fusion surgery, where your job is to insert screws into a patient's vertebrae to anchor them together. Now, if you just finished up lunch and you're a bit squeamish, you might want to look away, but after the surgery, your patient will look something like this. You might notice that not much of the spine is visible. All you can see are the very tips of the vertebrae. Plus, you're inserting these screws into the vertebral pedicles, which are highlighted in pink and surround the spinal cord, where a misplaced screw could paralyze a patient. So it's unsurprising that residents find these surgeries difficult to learn. There's over 3,500 residents in orthopedic surgery nationwide, and eventually they'll be performing over 450,000 spinal fusions per year, making it imperative that residents learn these surgeries effectively. Currently, residents are trained by inserting screws freehand in cadavers with no computer guidance, but that isn't the soundest method because residents misplace up to 29% of the screws they insert. Practicing surgeons, to minimize screw error, use tools like the Medtronic O-arm, which periodically acquires a CT scan of the patient during surgery and displays that to the surgeon. But at over $1 million, it's too expensive to buy just to train residents, and it doesn't provide the real-time feedback a resident would need to learn the surgery and exposes the patient to excess radiation. So where does SpineGuide fit into this? SpineGuide is a training tool designed for surgical residents, which is low cost and provides real-time feedback. And if it can achieve surgical-grade accuracy for eventual use in real procedures, it provides the added benefit of having no ionizing radiation. So how does SpineGuide work? We begin with a set of physical models of the lumbar spine, of which we have 3D scans, simulating a patient's preoperative CT scan. We convert those to point cloud models, collections of points in the same shape as the 3D scan. During a simulated surgery, we image the patient's spine, represented by the physical models, with an Xbox Kinect, a 3D camera primarily used as part of a gaming console. We then match the image from the Kinect to the point clouds generated from the 3D scans to track the spine in space. We're also tracking a wand tool simulating a drill bit that a resident can hold. And with all this together, we can display to a resident the current screw path and alert them if that path pierces the spinal cord. And now, Mike will show you all of this in action.
Thanks, Nick. So in order to give everyone a good idea of the SpineGuide workflow, we prepared a trio of demo videos. This first one focuses on initial setup. As you can see, you can choose any combination of the lumbar vertebrae labeled L1 through L5. Once you do this, the Kinect will take an acquisition and present it to you in the form of a point cloud. Then, using MATLAB's data cursor tool, you'd select the tips of each of the vertebrae and upload the coordinates to the software. This is a necessary step because in order to perform our live registration, which is the matching of each model's point cloud to the Kinect's point cloud, we need to start out with a very good initial guess at location and orientation. These coordinates give a good guess for location, and at the end you'll see that I select that the head of the patient would be facing to the right relative to the Kinect, which gives a good guess at the initial angle. Once this has been set up, a 4-panel screen opens up consisting of the point cloud with the model clouds superimposed on top. There's a general cloud as well as the front, right, and top views for a given vertebra. In order to demonstrate our program's robustness to intraoperative vertebral movement by the resident or surgeon, we're going to open up the technical details window in the GUI. This window shows the rotation in degrees about the X, Y, and Z axes. You're going to want to pay attention to the value for X because as you'll see in the live video to the right, we're going to rotate the entire thing about 5 degrees. Once the software updates, it'll have a roughly 5-degree reading. We then later on move it 10 degrees in the opposite direction, and you should see that X value of about 5 change to about -5. It's important to realize that if a resident or surgeon came in with the wand tool right now, they would be occluding partially or fully some of these vertebrae from our single camera viewpoint, which would make tracking them impossible. For this reason, at the beginning of our third video, where we demonstrate our wand tracking algorithm, you'll see that we start by pausing vertebral registration and making the assumption that the bones won't be moved around too much. A group member comes in with the wand, the trajectory of which will be mapped out by this black line. As you can see, when the black line intersects with the spinal cord, the screen flashes red. The group member is going to move to the L3, so we can select the L3 from our pull-down menu, which changes the focus of the front, right, and top views from the L1 to the L3. Now, in each of these demo videos, the entirety of the spine is visible. But if you recall from Nick's earlier slide, that's really not the case in practice. To more closely resemble the surgical setting that SpineGuide would eventually be used in, we took this red cloth and cut holes in it just wide enough for the tips of each vertebrae to be visible to the Kinect. We then performed a more in-depth angular analysis, sort of similar to the second demo video that we showed, and we found that we were actually able to get an equivalent accuracy with this setup as with the fully visible setup used in each other demo video. With that, I'm going to pass it over to Gurjeet, who's going to talk about our design goals.
Thanks, Mike. So our first and most important design goal is accuracy, and ideally we want to minimize any error related to accuracy so we can provide the most utility for residents and down the road surgeons. To that end, we set an objective of less than 2 millimeter total error, which is a standard in literature, and also the range that defines surgical grade accuracy for screw insertion. Now for us, there are two forms of error that contribute to this value. The first is registration error, which as you can see is a distance between a point on a 3D scan vertebra to a corresponding point on the image from the Connect. And we are happy to report a distance of just 0.4 millimeters was achieved. Second form of error is wand tracking error, and this assesses our ability to accurately track the wand in 3D space. And we evaluate this by measuring the distance between the tip of the actual wand to the tip of the average perceived location of the wand. And through testing, we achieved a value of 5.1 millimeters. And we believe the reason for this larger number is that because we only used one Connect that was mounted directly above the spine model, any occlusion of either of the spheres on the wand would result in some inaccuracies when we're actually trying to find the centers of those spheres. However, we do believe we can improve on this value, and solutions to that will be discussed later. We then have latency, which is the time it takes for a software to register and display a real-time action. And through discussion with an orthopedic surgeon, we agreed an objective of less than 2 seconds is appropriate because that's approximately the time they say it takes for a surgeon to look at the monitor, perform an action, and then look back at the monitor. And we safely hit this mark with a mean latency of 1.66 seconds. Now to give you a point of comparison, the Medtronic's O-arm can take up to 46 seconds to fully scan the patient and provide the same important information that our system can regarding proper screw path. Furthermore, we are very confident that once we can test our system on workstation-grade equipment rather than just personal laptops, that this latency will continue to come down. We then have skill level of the user, and we set a goal of only wanting a low skill level required to actually use our system. This would indicate that it is easy to use, and this is crucial because we're trying to make spine surgery easier, not further complicated. And to test this, we asked 12 participants to watch and navigate our GUI to assess the ease of use, of which 92% agreed that it was indeed easy and intuitive. And this confirmed for us that a resident down the road will not need extensive background knowledge or training of our system in order to use and understand what it is showing them. And then we have weight of the wand, and this is important because an unnecessarily heavy tool may become difficult to use, and we want to avoid this, so we set a goal of less than 8 ounces, which is in line with other tools used during spine surgery in the OR, and we safely hit this mark with a final wand weight of 1.28 ounces. Now with that, I'll hand it over to Jess, who will walk us through the setup.
Thank you, Gurjeet. Our testing setup consists of a mounted model of the L1 through L5 vertebrae onto servo motors for rotation control, along with an 80-20 aluminum rig to hold our Connect directly above the table, similar to how it would be in an operating room. These materials, while not included in our finalized product, were imperative for testing. Our finalized product consists of both hardware and software components. In terms of hardware, our cost of materials include the purchase of an Xbox Connect, adapter, and our custom 3D printed wand, for a total cost of $325. That, along with our annual software installment plan, when compared to what teaching hospitals spend annually to train a single resident, will be inconsequential, and therefore our product will be easily adopted into the healthcare system. Additionally, if our product reaches the operating room, it is an insignificant cost when compared to what it costs to purchase an O-arm. To recap, our current workflow involves initial registration, followed by live updates of both individual vertebrae and wand tracking. However, we see our product becoming part of a larger workflow in the future to include additional preoperative features, such as CT scan conversion to point clouds, as well as a more robust preoperative screw placement planning system, in which the surgeon can then intraoperatively check to see if their screw trajectory follows the intended path, thereby avoiding piercing the pedicle, rather than just spinal cord detection. Additional improvements we look forward to making are using our wand as an attachment to a surgeon's drill to better simulate to a resident how it would be like in an actual surgery. We also would like to use IR reflectiveness rather than colorimetric tracking, as this will decrease our latency and increase our accuracy. The addition of another camera at a different position will also increase wand accuracy while increasing our robustness to occlusion by the surgeon's hand. In the short term, we look forward to cadaver testing and training with residents. However, in the long term, if we are able to prove surgery-grade accuracy with our device, we see SpineGuide having the potential to gain additional application in the operating room itself. To sum it up, SpineGuide has developed a training tool that is both resident accessible and provides near instant feedback. Additionally, if SpineGuide can gain application in the operating suite setting in the future, where radiation will become a relevant factor, our product has the benefit of no ionizing radiation. Our orthopedic surgeon mentor has given us feedback that SpineGuide utilizes inexpensive components to simulate complex surgical navigation systems, which will be of invaluable use to trainees as they expand their skill sets and increase the safety of surgical care. Finally, we'd love to extend our thanks to Drs. Josh Baxter, Michael Haas, Andrew Milby, Michael Risk, and Seville and the rest of the bioengineering lab who are here with us today. We'd love to entertain any questions. Thank you.
What barriers do you see in terms of getting this into live surgery already?
So right now, our main barrier, as you saw in our design goals, was that we're not able to achieve accuracy within 2 millimeters, which is considered a critical breach. Some of the recommendations we gave before on how we would increase our accuracy, we believe would help with that.
So it's just a matter of the accuracy of it, or are there other kinds of things that would get in the way of it being allowed to be used?
So the accuracy is a big part of it in terms of our product being viable for use there. But then, of course, with any medical product entering an actual surgical space, there would be countless, potentially years involved trying to figure out how to get FDA approval with the medical device. Because as far as I'm aware of, there is no sort of prior art or anything like that.
Yes.
Yes, two questions. How is the unit actually calibrated? Is it important that the positioning of the spots device be in a particular position, or is it calibrated in any one of a number of different positions? And then follow on, we have the wand, but how does that benefit the resident once he's actually drilling?
Right. So.
During the game of operation,
So to the first point, right now we have the Kinect mounted directly above the patient or the cadaver. And in terms of getting the proper calibration for that, it could actually be at any angle. It has, internally, basically the point cloud that it would spit out after an acquisition would have the same coordinate system, regardless of where we placed it. It's just easiest, and I think we decided it was most realistic to place it directly above. It doesn't need to be the same distance away each time, because basically we inform it as to which section of the point cloud is relevant at the beginning when we select the tips of each of the vertebrae. As for your second question, the wand, you're right that in its current capacity, it wouldn't be a matter of using the wand and holding it up next to the drill. It would be more so that the resident could get an idea of, if I were to take the drill and put it at this angle, would this be successful? Like, this looks like a good angle to me. Let me look at the screen and make sure that I'm not actually piercing the spinal cord. But again, one of our future improvements would be attaching it to the wand, or attaching the wand to the drill, which would allow for a more seamless integration there.
And the feedback that they get is how the wand itself, are they looking at a screen, or is there actually an audible or light type signal?
So right now, they would be looking at the screen, and it flashes red if it pierces the spinal cord, but it would be fairly easy to add some other sort of marker to let the resident know.
Well, thank you.